Today we're going to take a look at some debugging techniques that will hopefully be useful to you in debugging your own programs. Debugging is the process of removing errors or bugs from your code. This process can often take much more time than writing the code in the first place, so it's important to have some tools at your disposal. For our first example, we're going to look at this program that we saw previously. I have saved this in my fakezod as a naked generator, which I will run now. This generator produces a list of numbers from 1 to 1 less than the number that we gave it as input. There are several very common kinds of errors you will encounter, the first of which is logic errors. Logic errors are simply when you have intended to write a program that does one thing, but ended up with one that does something else instead. The program will compile perfectly and run just fine, but the output won't be what you expected. In this case, we could imagine that we originally intended to write a generator which would produce the list of numbers from 1 up to and including the number we gave it. This would be an example of a logic error. Let's take a look at our second generator. Here we have an almost identical generator. However, the conditional of this has been modified. We can imagine having made this modification in order to address the problem of 5 not being included in the list. Let's go ahead and run this program and see if it fixes our problem. In this case, we're getting back sig, or the empty list. This is clearly not what we wanted either, so we still have some sort of a logic error in our program. Let's take a look at the code and try to read through it and see what the problem could be. We first create a gate that has one element in its sample, and we've given that the face and. We're then going to add a new atom to the subject with the face of count and a value of 1. Next, we're using cathep to indicate that this is going to be cast into a list of atoms at the end. And we then have our conditional. If we simply read this conditional, we have greater than end count. Now end, recall, is the number that we passed in, and count is our counter that we defined up here. Now when we first run this program, if we gave it a value of 5, end would be 5 and count would be 1. This conditional would then read if 5 is greater than 1. Given that 5 is greater than 1, we proceed to this clause of the statement and produce sig. It can often be useful to examine the state of your program as it's running. While Hoon currently lacks the best tool for this, a breakpoint debugger, we do have a special rune that we can use that can help us out. That rune is sigpam. Sigpam takes 2 expressions. The first is a thing to print, and the second is the rest of the program. So in this case, let's print out count and see what that gets us when we try to run this program. Here you can see that 1 was printed out. That's the value of count when our program was running. You'll notice that this time there was no output from the sigpam. This may throw you for a loop initially, but the reasons are fairly simple. One of the important parts of the Urbit system is forward, which is our build system. Forward does a very good job of caching so that it doesn't need to rebuild things unless it's necessary. This is generally extremely useful. However, it can be mildly off-putting when we're writing a naked generator. What's happening is that sigpam is a special rune called a hint that's only being run when it's built the first time. After that, the value of the generator is cached, and on subsequent runs, it won't be rebuilt, which will cause the hint to not print out. You can see that if we change the input, we will still get an output for sigpam. This is also only a problem with naked generators. Once we get into building say generators, this problem will no longer exist for us. To use sigpam with a naked generator, you're either going to have to change the input to be some value you have not yet used, or modify the program in some way that would cause Forward to recompile it. It turns out that the problem here is that our conditional, in this case, greater than end count is actually backwards. We could fix this by reversing the order of end and count. We could also fix this by replacing greater than with less than. So let's save and run that generator now. Here you can see we've gotten the same list as we expected before, except now we have 5 on the end as we intended. This is a fairly simple example of a logic error. Debugging logic errors can often be very difficult as it requires you to build a mental model of what your program is doing and carefully compare that model to what the code says. Being able to read through your code to find errors takes a lot of practice. As an analogy, think back to when you first learned to read English. It took you a great deal of time to do that. Here too, it will take you a great deal of time to learn how to very quickly read code. Please do not worry if you have trouble doing this initially. Let's take a look at another one of our generators. Here we have an almost identical generator to the one we just ran. We can see that we have already fixed the greater than error that we had before. Let's go ahead and run this new generator and see what happens. Here we see another common error that plagues programmers at all skill levels, the syntax error. The syntax error is just what it sounds like. You have written some piece of code that isn't syntactically correct. Because it's syntactically incorrect, the compiler is unable to interpret your program and therefore crashes. We get a specific line and column number where the compiler believes the error originated. Let us take a look at our file at line 9, column 1. We can see that line 9, column 1 here is actually the end of the program. If you've had some experience with this before, you may immediately notice what the error is. Syntax errors in Hoon are almost always either giving a rune the wrong number of arguments, or forgetting to add a terminator on a rune that takes a variable number of arguments. Have you spotted the error yet? The problem is actually on this line. Coalesce is a rune that takes 3 expressions, but it actually has only been provided with 2. The compiler shows the error as being here, where it's expecting the 3rd argument, but our actual mistake was up here. So it's important to read backwards in your code and see if there are any errors above where the error message appears, because it may not be telling you exactly where the problem is. For the sake of argument, let's say that we've been staring at this code and we just can't find our syntax error. We can't spot the problem just by looking at it, so we need some other tools to help us along. One thing you can start doing in Hoon is take some section of your code and simply comment it out. Now, having commented this code out, our entire program will actually still fail because whatcall takes 3 expressions, and we've cut out the final expression. So we need to replace this with a dummy value that is of the same type of what would be produced by the expression we commented out. In this case, we need a list. So we can go ahead and type this list in here, save our program, and then try and run it again. We can see that we got our dummy value. So given that, we know that the syntax error must be somewhere in the commented out code. If we still got the same error, that would indicate to us that the error was still somewhere in the uncommented code. One important point to note when writing Hoon is that there is currently a problem where if the final line of your Hoon file is a comment, you need to have a blank line at the end of that file. Otherwise, the compiler will complain about a syntax error. This is actually a bug, so it will get resolved eventually, but it is something you'll have to deal with for now. Given that we know the error was in this section of code, we can begin to cut it down further by commenting out sections of that. Here I've chosen to use the dummy value of 4. It doesn't really matter what your dummy value is, you're just replacing it with something of the same type. We see that we still get the same error, so we know that our error is still somewhere in our code. As we've seen previously, we know that this is actually the coalesce that is the problem. It needs to be coalhep instead, as there's only 2 arguments. Here's yet another variation on the generator we've been looking at. Let's go ahead and run this version also. Now we encounter one of the other most common types of errors that you will see in Hoon programs, the nest fail. Nest fail is actually a type error. You can think of a type as a hole in a piece of wood. It could be round or star-shaped or square. That doesn't matter. The fact is that it is a hole of a particular shape. You can imagine the data as a peg that we're trying to put into that hole. If the peg doesn't match the shape of the hole, it's not going to fit. This is what a nest fail is. It's an attempt to put some data that does not fit into a particular type in a type. In other words, the type of one thing is not nesting within the type of another. Let's take a look at our program and see if we can find the problem. You should notice that we have been using ket-hep in all of these generators. Remember that ket-hep is our cast operator. It's a good habit to get into to cast the output of all your gates. While in many cases this is not strictly necessary, it can be a helpful guidepost to someone coming behind you so they can quickly see what type your gate is supposed to be producing. Let's go ahead and remove this ket-hep and see if we can run our program then. So now we can see that our program actually does run after that ket-hep was removed. Does this mean that the ket-hep was an error? No. The error is somewhere else in our code, but by removing the ket-hep we can get some output from our program that can help us to debug it. Here you can see we have a cell, the head of which is 1, and the tail of which is another cell. You can traverse down this and see that everything is in the same shape as you would expect for a list, except for one thing. The final element of every list has to be sig, or null. The final element of this is 1. So casting it into a list proves to be impossible as its final value is 1, not sig. Let's restore the ket-hep. If we read through our code, you can see that the highlighted number 1 is the end element of the list. This is because this is the only branch where we don't call our gate again to continue adding numbers. This needs to be sig.